So today's lecture is about an introduction and overview to quantitative big imaging, what it is, and I will also tell a little bit more about what you can expect for the future. And a little bit also motivating what quantitative methods are in imaging, what's in imaging, whether they come from, a little bit more about science and reproducibility, and I will round this lecture off with some workflows or ideas how we can work with the data. And this whole course will be based on using Python, and in order to run this particular notebook, I always have to execute this block of importing modules, some code that right now I'm not going to explain a lot about, but it's needed for running the following notebooks or the following cells in the notebook. And once that's run, you can see how the code is executed if I have code in the slides. So first of all, a little bit about the course. I'm going to introduce who we are giving the lectures, what I think you are, why this class at all exists, and then you can see a little bit also about how the dates will be distributed. So first of all, me, I'm Anders Kästner, or just plain and simple Anders. I'm a beamline scientist at Paul Scherrer Institute, working with neutron imaging. And I also give these lectures at ETH. Before that, I was also working as algorithm developer at the Variant Medical Systems in Baden. And then I came from ETH working with soil and soil physics, which was actually an introduction to working with this large-scale facility imaging techniques. Before that, I did my PhD at Chalmers Institute of Technology in Sweden with the topic image processing and signal processing. And here below, you can see my email address as well. Then as teaching assistant, I have Stefano van Gogh, and he is a PhD student in the X-ray microscopy group at ETH Zurich, and also at the Swiss Light Source at Paul Scherrer Institute. He will support you during the exercises, and actually you can probably see him somewhere among the pictures in the sidebar. He's waving now. And well, he will help you through the exercises. I will too. And also we will talk about how the exercise will work after this lecture session during the exercise. So what I expect you to be is, well, you will have a pretty wide spectrum of backgrounds. Some of you are engineers, physicists, others are scientists, students in art history, some are even computer scientists. And with these different backgrounds, some of you have very little background in how to work with images, how to work with programming, etc. So some maybe say, oh, I may have heard of something called Python before, and possibly you can do some programs with it, up to the level that you are pretty good at coding and writing even C++ code and hand code optimize afterwards, etc. So there are very different backgrounds among you people, and I'm trying to meet the needs of everybody of you, and let's see how it works out. So it's a big stretch. What we will have is a lot of conceptual image exercises where you more look at the steps to execute. Of course, you will write some code lines to achieve this, but most of it should be in a way that you get the introduction, what you need to do, and then you have to fill out some changes or maybe write a couple of lines to solve the exercises. Of course, you can also start doing your own great projects, starting doing your own coding if you like, but then we will look into that separately, in particular during the projects that you will do if you would like to. So usually we have one lecture set per week, and no, exercise set per lecture, and these are optional. You don't have to do them. I'm not going to take notes. This and that one did it, this one did it not. So it's more for your understanding how the things we talked about during the lecture are supposed to work in the real problems. We're going to do it using Jupyter Notebooks, which is an environment where you very graphically work with the programming language Python. You can, of course, also write your own Python scripts. You can write JavaScript, C++, whatever, but what we are supporting is these notebooks. And this is the way we mainly work. On top of that, we have the science project, which is also optional. But if you really want to get into this, it is actually strongly recommended that you try doing a project of either of your own definition or something that we provide for you. These projects could be, I saw that there are pretty many PhD students, so it could be a small fraction of an analysis problem you want to solve within your PhD project, or for master students, something that could be relevant for your master project. So this is pretty open what you're going to do. It's about 3 weeks, I think, of not full-time work, but that during 3 weeks we are going to work on these projects. And afterwards, we'll round off the whole course with the presentations, how you show your approach and how you analyzed and what the results are. Well, that I already said, essentially. So, and one more thing about this project, I am going to give you the chance also to use the project as a discussion base for your exam. So the exam of this course is an oral exam, and we can I will then take different pieces and take that as a starting point, and that gives you a good starting point also for your exam. The whole course is, well, now I see there is a little mistake here. It should actually end up in June. But I think it's around the segmentation part. There should be a shift, but otherwise it's essentially every week on Thursdays, this time, 2 hours that I'm going to give a lecture. And well, there are some breaks, for example, Easter and Ascension, where we have a day off. But otherwise, we will just go on every Thursday with these lectures. There are some things you can read. Actually, I didn't update this one. I see some book on image processing with Python. I have to bring you one suggestion on a book here. But otherwise, there are some articles to look at out on the web. So you can just click through, get you an idea how other people are working on it. On top of that, there are some books too. One is the book by John Ross, Image Processing Handbook. It's a pretty thick and heavy thing, so I don't recommend you buy it and carry it around in your bag, because that will break your back. I think it's about 1,200 pages or something, but it's available online, so you can download it if you are in ETH network. Jean-Claude, Morphometry with R, is also a book that you can get through ETH library. So it gives you some ideas how to measure items and images using the programming language R, which is not really the one we are using, but it has a lot of interesting things, and you can actually pretty straight off transfer this information into Python. The same commands are available also in Python. So it's more about looking at the theories they are talking about in this book. So much for background and practical things. Let's take a look at what we are really here for. So you have data. You are very happy you got your experiments. You could put your little sample on top of the stage in an imaging beamline. Then you produce data, a lot of it, gigabytes or sometimes even terabytes of data. At some beamlines, you produce plenty terabytes over a day. And then you have this very confusing, overwhelming task. You have to bring something out of the data. And at the start, I see very many first-time users. They look like scratching their head and how should I approach this stuff? And this is where we're going to give you a toolbox of methods how to work with the data. So let's look at some kind of workflow. So you have your images, you make some images, you have your sample, you make the images, then you do some algorithmic analysis, some fancy stuff, some magic stuff, and then you do some even more complicated stuff, and then you do some math, and well, everything is just stuff, and you don't really know what you want to get out of it. But in the end, you want to have a nice headline in Blick, for example, saying science says that ice cream is good for bones. Okay. We want to make this stuffy thing into more real workflows that you really can work with. And not only for single image, but it should work also for 10 images or 100 images or 1,000 images. But you shouldn't work 10 these times more. Of course, the computer will work hard, but not you. So that is the goal here. One thing is when I talk about many images is that today's detectors and fluxes as different beamlines give very high acquisition rates. And that is something that can produce loads of data. So for example, a typical detector does 1,500 or more frames per second. That would give 8 gigabytes per second. Many tools that we're working with, like MATLAB, Aviso, Python, they saturate the memory within 60 seconds. So you can see there is a pretty big skew here. You can't do any real-time analysis on this, at least not saving it and definitely not doing a full analysis. Then you also have some single camera things that you can actually, there are cameras that produce more information per day than the whole Facebook user community, or others that produce 3 times as many images per second as they are uploaded on Instagram. So it is really huge amount of data that is produced on a single place with a single device. And that's afterwards your task to take care of. Facebook and Instagram, they have big staffs working with this and you are alone. So it's a hard situation. Then we have different sources of images, depending on what you are going to, what kind of experiment you're doing. You have, for example, X-ray based, where you have tomography, where you produce more than 1,000 frames per second and getting several gigabytes or CSAX diffraction patterns, 30 gigabytes per second, or even a nanoscope, 10 terabytes per day. Typically, you buy a hard drive in a computer is half a terabyte, or maybe if you have a big one, 2 terabytes. So it's a lot of data. And also each file is several gigabytes, tens or hundreds of gigabytes large. In optical methods, you work with light sheet microscopy. Then you produce maybe images in the rate of 500 megabytes per second. So it's not that bad, but still it's pretty much. Or high-speed confocal microscopy, 78 megabytes per second. Then we come to some personal devices like the GoPro, 60 megabytes. And it's actually a pretty cheap device. So it's about $600. And the other environments, they cost pretty much. So if you're talking about an X-ray beamline, you're talking about millions. Or else there is also the FPS 1000 camera, which produced 400 megabytes per second. It's even cheaper, so it's $400 for that device. So you have very many different sources of images, but in the end, you have images in some kind. And for that, we have some kind of experiment life cycle. We have the experiment design, finding the right technique that you need to get the data, how you have to prepare your samples, and also more experienced scientists also demand more complicated techniques, and also, so it's actually techniques and scientist demand is growing with time. Then we have the measurements, and there are different acquisition speeds, and that, as we have seen already, depends on the rates, depends on which detector we have, but detectors always get faster because technology is changing. Then we come to a task that you may not think about, but the management of the data, like storing, backing up, moving around, setting up databases, how to know how to work with the data. This has been automated with time, but still, you have a lot of data to handle, and that needs to be calculated in the whole process time. And then, of course, you have the whole process, post-processing, and it's a very time-consuming task, as you can see on the next slide here. This is actually a kind of a mix of speculations and real observations. But anyway, you have at the year 2000, you had pretty much time spent on the experiment itself. The detectors were not so fast, and with a beam time, you could maybe expect to get at a X-ray beamline, you could maybe expect 1 or 2 samples per day. And it took a long time to get the data. And as it took a long time to get the data, you also didn't produce that much. So the management part was not so big. But afterwards, you have a pretty big chunk of post-processing still. When we go 8 years ahead, then situation changed. We got faster cameras, but still, and faster cameras also produce more data. So the management part is growing. And also the post-processing is growing. The sample preparation part remains about the same amount of time. But you can see here that with even faster techniques, we get more on less time spent on the experiment itself, which could be a couple of days, but then slushing around the data and organizing the data in a correct way, that takes very much time. And also the post-processing is still more or less a constant throughout time. The question is only how long time it took to produce it, and also you have to consider that we have a lot faster computers than we had back in 2000, but still there is a long struggle to get the post-processing through. It has different reasons for it, but one is being able to produce the code that can do it, but the other one is actually it takes time to put a lot of data through the computer. So let's look at the handling of masses of images. So first, what is a terabyte really? So if you looked at one image, 1,000 by 1,000 pixels, that's a 1 megapixel. And it could be something like the one I created here. It's just 1,000 by 1,000 pixels with random noise, nothing particular. But if you would like to look at this every second, then we have 1 terabyte is 10 to the power of 12. And the image size in, let's assume also we have a 16-bit image. So we have 1,000 by 1,000 pixels and 16 bits by 8 because to get the bytes. And an hour is 60 by 60 times 60 seconds times 60 minutes. And if we now compute the time per terabyte, we come to the point that it takes almost 140 hours to look at one image every second to see a terabyte of data, which is pretty long time. And of course, the computer can do it much faster, but still, it is a considerable time. On top of that, it's not just looking at it. Let's say, what do you want to get? Maybe you want to count the number of cells in a bone slice and also ignore the ones that are a little bit too large or too weird shape. Maybe you want to count, are there more on the left side than on the right side? And are the ones right or left bigger, or is it top and bottom? What kind of distribution do you have of the sizes? These are questions you would like to know from the images. And getting this idea, well, you can do some kind of qualitative assessment saying, oh, well, it looks like they are big on that side, they're big on that side. It's approximately 200 cells, but you can't get any sure numbers. And this is on a single image, and already doing this assessment takes more than a second. So now if you would have a terabyte of slices, that's a long time to look at. You probably will spend your whole PhD on looking at one single data set. So now for statistics, we do actually need more samples. So we can't just look at a single slice and say that, well, this is a fact. Now we need really to look at several images. So in this case, you can see a panel of 96 samples. And not only single slices, but also in 3D with 2,000 slices instead of just one. And now again, we come to the problem, what is now, can you look at it qualitatively and get a reliable number? You can't. And also within some limited time. And then to do it really complicated, we want to add not only within one population, but we want to have several populations of ages, genotypes, etc. And then you land up in over 1,000 samples. And how should we handle this amount of data? It's a huge thing to work with. And this is then an obstacle you have to solve if you are doing this kind of experiments. And then we have to define some metrics to do actually a quantitative evaluation of the data. And maybe you are asking something that is more soft than just hardcore. Is it small? Is it big? How many are there? You can maybe ask about things like, is something more or less aligned? Yeah, that's starting getting tricky, and you have to actually put some kind of numbers on what is more or less aligned. And this is something we are also going to look into in later lectures. Then to make it really fun, we have dynamic information. So we do a time series analysis of, for example, some foam where you see the bubbles rising. So what you see in this movie here is actually the pores between the bubbles, or the bubble walls in a time series. So this is a three-dimensional image of a foam. And now is the question, how fast are these bubbles moving? Do they all move at the same speed? Are big bubbles moving faster than the small ones? Or is there some boundary effects, like do bubbles near the edge move slower? And also, how are they rearranging? Some bubbles are popping and merging into one, and so on. Questions like this is actually produces four-dimensional data, which makes it even more complicated to analyze. So I've been talking a lot about images, and maybe I should give you a little bit some words about what are images at all. So a very abstract definition of an image is that it's a pairing between some spatial information, so we know where it is, and some other kind of information, a value or something. In most cases, we're talking about 2- and 3-dimensional positions, so x, y, and z coordinates, and a numerical scalar value, the intensity. How to get this into an image? The computer is, as you know, can only work with memory positions. So you need to arrange the image data in a matrix array. But the real world, on the other hand, is continuous. So you have continuous intensity fluctuations. You have no boundaries. So I mean, around the samples, the world goes on. So you have to bound yourself. And what you need is to actually use some sampling to get the image into the computer. First thing is the position. So we need to localize some small region, which is the pixel, the smallest element in the image. And each pixel also consists of discrete levels to get the values into the bits and bytes of each pixel. So you have different levels of discretization here. So the pixel intensity and the position both need to be discretized. And that is what's happening in the sampling in the camera. So you don't have to care much about it, but just be aware that doing it the right or wrong way, you can get the wrong sampling and you don't see what you want to see. So what does it mean? So one thing is we have an original image. So this, let's say this is what comes in from the camera. But sometimes, for some reason, you want to downsize it by a factor 2 in both directions. It looks still pretty same. But if you downsize it 32 by 32, may make sense for some investigations. But you can see now that it's getting harder to recognize the sample itself. You have very large pixels here. The other thing is you can also look at the sampling in the gray levels. So if you take this one, which was a 16-bit image, and then you squeeze those 16 bits into 4 bits, then you have only 16 levels, and you start seeing that it's getting a bit patchy. You can see regions around here, also these regions starting getting patchy. If you now go down to 2 bits and 4 levels, then you can, it's a really patchy thing. You can see that, well, here is a blob, that is a sample, and in that sample, there are some places that are different. So you have to be careful about how you set the number of gray levels in the image, and also how large the pixels are. You may need to do it 32 by 32 and with 4 levels, because otherwise you can't meet the time requirements or something like that. But you have to also be aware at that time that the analysis will not be easy, because you lose so much information by doing so. So let's create a little image. What I'm doing here is, with this little Python code, I'm creating a random image with a size 5 by 5, and that is by choosing values in the range of 0 to 100, or 99 actually. Then I create the image out of it, and we can see here that we have the positions X and Y. 0 is then 86 intensity, and at X position 1, so we're just stepping along the first row, 99, and you can see that it's just random numbers. What comes next is we want to show it not only as a table, but as actually an image. So here we can see a first display. It's a gray level image where you can see how the values are fluctuating within the image. You can see here the color bar showing what each color corresponds to in actual values. And this would be a very simple first image. Then we have different ways of showing these images. So if we have a 2D intensity image, we want to maybe apply a color map, also called color lookup table. And for one thing, it's maybe looking more exciting than just the grayscale. And actually some features are easier to detect if you put some colors on it. And this paper from '96 tells you about how to choose the color map depending on what you are looking for in the data. And let's try, for example, a color map called blues, so different shades of blue. And in this show, I even show the pixel values within each pixel. This is possible if you have a small image like a 5 by 5 or maybe say 20 by 20, then you can still look at the individual values. But if you have a 2K by 2K image, you will actually clutter the whole intensity information by the numbers you try to display. So that doesn't work. So this is a tool you can use if you have small images. Maybe if you want to investigate what's going on around a certain feature, you can do it like this. And if you're doing algorithm development, it may also be relevant to show the pixel values in this way. Then we can play with a lot of different color maps, like a very old one, which was long time popular, called JET. It's some kind of rainbow colored color map. And actually today it is discouraged from using it because it's very hard to interpret what it actually means. Then we have one that is called HOT. It's kind of a grayscale-like, so it's a continuous change from low intensity to high intensity over the color scales. And this actually is easier to interpret than the JET map. And it's even the way that you should never use the rainbow color map. It's not good for printing, it's not good for interpretation. And of course, we have a lot of different color maps available. And now to show all these maps, I can't scroll here. So I actually leave the slides. And now we can see here that there are pretty many different color maps already predefined within Python. And some are even there just to do qualitative assessments of the data. You can use it, for example, when you do also done some segmentation just to mark out the segments. And well, there's this. It's a big playground, and what I said before, never use the rainbow map like JET. And there is even a paper here about why the JET map is not good. There are some people looking at the human perception of different colors and also involved color blindness as one of the factors how to define a color map. And today, let's see if I can find it. The one that is default in Python and the matplotlib module is the called Viridis. In MATLAB, you have one called Parallax. I don't know if they show it here, but it's pretty similar. It's almost the same, but a little bit different. But this one is one of what the color perception scientists have developed as the recommended color map to use in your publications and presentations. So let's go back to the slides again. No, that way. So how are now the colors combined? We have in our different color maps, you can see here I'm plotting some dots, how the red color component, how the green color component, and the blue color component are mixed in order to get different color maps. So the computer is usually working with a color space called RGB, which stands for red, green, and blue. It's a traditional old color map system, and that's what usually is used by most programs. There are a lot of other color spaces that you can be using. For example, for printing, they're preferring using a different. For example, if you look at your laser printer, or also on your, if you have still an ink printer, that one would work in yellow, magenta, cyan color space because that's easier to combine when you work with pigments. So let's apply some of these color maps. You can actually also mix up your own color maps. Looking at this case, we have the linear mapping. So you would actually take the values one-to-one into the lookup table. But another thing you could do in order to focus on different parts of the image, you could also work with a logarithmic mapping for the colors, which makes sense for some experiments or some data, depending on what you want to highlight. And here you can see what it does. So we have the grayscale lookup table. We have some hot map. And if you look at the lookup table with the logarithmic in it, you can see that it highlights more the bright areas here, but the dark ones, they are not so emphasized in the middle here. You maybe do some kind of compression, so there is not so big contrast difference between the dark and the bright. May make sense for some visualization. And with that, it's actually already 10 o'clock, and that would be time for a break, I believe. So I don't know what you are used to, but normally it should be 15 minutes, but do you mind if we just do 10? Please raise some hands. Or thumbs down, whatever. So at least I got one thumb that I can see, so that's good. So yeah, great, many thumbs. So okay, let's do a 10 minutes break. I'm switching off my microphone, but if you want to ask something, just speak in and I will be just here.
There was a question on chat.
Ah, okay. I missed that one actually. There it is. I can write it. So there is I think it's Parallax. And that's also the default color map now. And I think Parala is actually named from a bird which has about the same color mixing in its feathers. Viridis, I'm not sure really where it comes from, but I think it could also be a bird, but I'm not sure. Actually, there is one lecture about the Python color map. You can actually look for color map on YouTube and color map Python something. And there is a great, yes, of course. This color map is really recommended over the rainbow map. If you ever try to print a rainbow map, you will see it's very confusing, in particular if you do a grayscale printing. You will see that it's very hard to distinguish what is now red and what is blue. They come about with the same shade of gray if you do a black and white printing. The other thing is if you look at Parallel or Viridis, they actually appear in black and white print as a continuous grayscale, which is very convenient.
Hello, hi. I have actually a question. I
Yes.
was wondering, is there any version containing project but without exam for those PhD who actually they don't need any grade or exam after the course, but they're still interested to participate in project exercise and lectures?
Just go ahead. Don't sign up for the exam.
Okay,
Yeah.
good. Yeah.
It has happened before.
Okay, thanks.
Well, it's not good for the statistics, so I appreciate if you go to the exam, but you can just listen in and do the exercises.
Thank you.